Okay, so today we're going to be talking about percent and also some of the related units such as parts per million, parts per billion, and all those related things. All right, so first up, here we have the percent sign. Okay, so this is percent. Okay, and we have seen, these percent signs all over. I mean, you just go to anything, in your coupon thing. I mean, you'll see 50% off, for instance, your sushi or whatever, your regular coupon. So, these are fairly familiar, but we're going to go into, how this relates, towards chemistry and things we're going to be seeing all the time. Okay, so as for percent, well, right here, the cent portion means basically 100. So the way we can interpret the percent is by saying that this is the same thing as saying parts per 100. Or this is basically, 10 to the minus 2, a fraction of something. So when we're talking about this, we're going to be looking here, and this is not just for percents, but everything else, is that we're going to be looking at a subset of something divided by the whole, and then we're going to multiply this by the 100%. And then this is going to give us, our number here, in terms of percent. Now what I'm saying here is subset and whole. So here we have our whole thing. So this is our whole thing. And then inside of there is our little subset. So the reason this is important here is if you just look at this, first of all, the subset is going to be smaller than the whole. And this is, very, very important because this means that when we're going to be dealing with using our percents, when we're looking at our subset here, the number here is going to be smaller than the whole. So in other words, if I have 5% of something, that means I'm going to have 5 grams of that substance in 100 grams of the entire thing. Also, when we're going to be calculating this, we have to be very careful that the subset is included as part of the whole. Okay, so the subset and the whole are, contained in each other. That's not outside of the whole thing here. So to explain this, let's just say I have here adding up 5 grams of salt, and this is your regular table salt, and that would be sodium chloride, to 100 grams of water, which of course is H2O, which everyone should know that, I hope. So if I take this 5, and you might just say, well, that's going to be obviously just a 5% solution because that's going to be 5 divided by 100. But remember, when you're mixing these two things together, you're now going to have this 5 grams of salt, which is your subset, in the whole, which is going to be the 5 plus the 100 grams. So this is going to be 5 grams of your salt divided by the 100 plus 5. And then you multiply that by 100%. So that's just obviously going to be 5 divided by 105 times the 100%, which is going to be 0.0476 times 100%, which is 4.76%. Okay, now I went through and did this kind of, longhand, writing out every little step. And when you get, used to this, really what you can just say is, all right, I'll just calculate this fraction 5 over 105, and then you just go here and move the decimal point over by 2 spaces, and then that's going to be your percent. So when you get used to this, and I may, because I'm used to this, it's very easy to just, write this out as the fraction, and then move the decimal point over by 2, and then you get your percent, rather than writing out the 100%. So you don't really need to write it there, but if you just need to remember it so you don't, forget about what you're doing, you can write it there, or if you just remember to move it over by 2, either way still works perfectly fine. All right, now how these percents are useful is, let's say we have here, let's say you weigh 70.0 kilograms, and you get your body fat taken, and you find out that you are 19.6% body fat. Okay, so our question is, how many kilograms of fat are on your body? So what we do is we use this percentage right here, and this is going to be saying 70.0 kilograms. And now this is saying 19.6 kilograms of fat per every 100 kilograms of tissue. And here these kilograms cancel out, and you're left here with kilograms of fat, which is the same thing here as just saying 70.0 kilograms times 0.196. Okay, that's exactly the same way of writing it out. So if we do this, we get here 13.7 kilograms of fat. All right, and again, when we're using the percentages up here, it's very, very important. You just notice here your subset, which is your fat, is smaller than your whole, which is the whole body, right? And that's, of course, fulfilling this thing we had up here. If we happen to do this the wrong way and we round up with more than 70 kilograms, that does not make any sense, right? It has to be smaller than what we're actually starting with here. Okay. Now, on the flip side with this, let's say you're a cannibal and you want to eat somebody, but you don't want to eat too much fat on the person and you're too lazy to trim it off. So let's say you're limiting yourself to 1 kilogram of fat. How much tissue can you actually eat? Well, then you in this case would be dividing this. So that would be 100 kilograms of your tissue. And you divide that by your 19.6 kilograms of your fat, which is the same thing as going here 1 kilogram of the fat divided by 0.196. And that's going to work out to be 5.10 kilograms of your tissue. Okay, so you only can eat an arm, but not the leg. Okay, so again here, notice we're using our subset here to figure out how much of this whole is actually contained in there. And again, your whole is going to be bigger than your subset. So my 5.1 is definitely bigger than my 1. So, we did this right. Because what's going to happen is when you're doing these kind of calculations, you may be thinking, oh, do I multiply or do I divide in these cases? Because it's very easy to accidentally do it the wrong way. And if you happen to do that, well, then you just step back and say, well, am I getting bigger or smaller, right? I'm starting here with the small thing of fat, which is my subset. My whole thing should be bigger than that. If it gets smaller, you did it the wrong way. Over here, again, like we said, the subset here has to be smaller than that whole. Otherwise, we did it the wrong way. So it's a very, very good way of just checking to make sure your answer actually makes sense. Okay. So this was percents, and really for the rest of these calculations, it's going to be the same thing, except for percents we're always going to be dealing here with the 100% sign, but for these other ones we're just going to be using other numbers, either 1,000, million, billion, or trillions. Okay. So this one here that you may have seen, it looks like a percent sign, except here we actually have 2 little zeros on the bottom instead of just the 1 little zero. This is called per mil, although it's commonly just written as per mil, like that. And here, if you think millimeter, that's 1/1000th of a meter. So this is going to be parts per thousand. And you don't want to write this as PPT. Okay, so that's not the same as PPT. Because PPT would be parts per trillion, although sometimes people do screw this up and say PPT is parts per thousand, which you have to kind of look at to the context of this. But really, the parts per thousand or per mil is the generally accepted way that you should do this. So here, 1 per mil is actually equal to 0.1% in this case. Okay, so then this parts per thousand right here, that's also, basically equal to 10 to the minus 3. So remember, percent was 10 to the minus 1, or sorry, 10 to the minus 2, and per mil is just going to be 10 to the minus 3. And by the way, if you happen to want to make this symbol on your computer, now I don't know how to do it for a Windows machine, but if you happen to have a Mac, you can do this by going Shift. So if you press the Shift key, then you hold the Option key down, and then you press the the R button right there. Okay, so don't worry, I shouldn't write that there, but it's basically the Shift Option R, and you can make that little symbol if you want to use it on your computer there. Okay. Next up is ones that you probably have heard of before, and this is going to be your ppm, which is parts per million, ppb, which is parts per billion, and ppt, which is, like I said, parts per trillion, LLION. And occasionally you might even see ppq, which would be parts per quadrillion. But that would be, very, very small quantities. So the parts per million is going to be, a million is, of course, 1/10 to the 6th, so that's going to be 1 over 10 to the 6th. So part per billion is going to be 10 to the minus 9, part per trillion is 10 to the minus 12, and part per quadrillion would be 10 to the minus 15th if you happen to be dealing with something that is that small. Okay. One thing that I haven't mentioned up here is when we're talking about, this part of the whole and the subset, over here we were dealing with this in terms of mass or weight. But there's other ways that we could also be looking at this. So mass and weight are the usual ways of looking at these, but we can also look here in terms of, so we're going to have the mass, or the weight, because it's usually done in terms of weight, or volume, or even in terms of the atoms. Okay, now this is why the SI system really doesn't like using the parts per million or parts per billion, but it's just so ingrained in the scientific literature that you really can't get away with it, is because unless it's explicitly stated, there's a little bit of ambiguity. If I'm talking about here, parts per million, parts per billion, or whatever, I don't know if I'm talking about this parts per million in terms of number of grams of substance, number of milliliters of the substance, or number of atoms of the substance. I don't know. There's a little bit of ambiguity right there. Now, to relieve some of this ambiguity, they use here, for instance, the ppmw, or the ppmv. Right? So this would be equivalent to your parts per million, but here you're dealing with the weight. And this would be your parts per million in terms of the volume. If you're dealing with the atoms, usually those are going to be maybe in terms of volume as well. That is dealing with the gas laws and stuff, but there is no specific thing if you're dealing here with atoms. It would just have to be stated explicitly. Now, how do we know, if is there like some general rules that we can actually deal with, if we're dealing with terms of mass or volume or atoms? Well, if we're dealing here with the weight one, this is going to be, if you're dealing with all solids. So if we're mixing up, how many, for instance, how many percent salt is in the soil, that would generally be done, because salt is a solid, soil is a solid. That would be parts per million in terms of the weight. Or if you're dealing with solids and liquids. In that case, just like we did before with the salt dissolved in the water, that would be, the percent, or it could even be parts per million or whatever in terms of the mass or the weight of that. If you're dealing with volume here, this is if you're dealing with liquids, or you're dealing with gases. Okay, and atoms, that can be, any of them. I mean, really, it just depends on what you're actually talking about in those cases. Now, you might be, it seems like there's a lot of ambiguity here. There's no like hidden, set rules that I'm actually talking about, and the reason is because there are no nice set rules for these. It really depends on, what scientist is reporting, what journal they're reporting in, what their subfield is, and everything. So you just have to, read the literature and figure out exactly what they're talking about, before just, giving an overwhelming conclusion based on one thing. So you just have to be very careful when we're dealing with these. Now here, if we're dealing between parts per million of weight and parts per million of volume, are these the same? No, that's why they do have two different symbols. And what happens if you want to convert between the two? Well, if you're trying to convert between the two, you're going to need the density at some point. We're not going to get into these, and of course you are probably wondering, well, what you're really wondering is if this is going to be on a test. How do I know which one to actually use. Again, I will state this explicitly, if you're dealing with in terms of mass or volume or number of atoms, then that will be stated explicitly. So don't have to worry about any ambiguity on, my tests. I will, be as clear as possible when we're dealing with these things. All right. Also, for here, just for an example here, if we're dealing with the number of atoms, you may have heard that the CO2 level has reached 400 and plus parts per million. Well, what they're actually talking about here is in terms of the number of atoms. It's actually, this is going to be equal to the number of atoms of CO2 per number of, I shouldn't say atoms, I should say molecules. Molecules of CO2 per number of molecules of air. And here the air includes oxygen, nitrogen, carbon dioxide, water, any other little gases that you may have in there. And what we're talking about here is the number of molecules of CO2, which again, is going to be our subset here. And then the whole thing right here is going to be the number of molecules of air. And since this is going to be in parts per million, then we multiply that by 10 to the sixth to convert this into parts per million for that. All right. So again, if you're dealing with these parts per million, parts per billion, parts per trillion, quadrillion, then you just multiply these. When you figure out the fractions here, you'll multiply that by 10 to the 6th, 9th, 12th, or 15th, depending on what you'd actually need. Now, if we're dealing with weights in these cases, just to kind of help visualize, what we mean by parts per million, because these units can be a little odd in some cases. Well, here a part per million is equivalent to having 1 milligram per kilogram. So that would be 1 milligram of your substance divided by 1 kilogram. It's going to be 10 to the minus 3 grams over 10 to the plus 3 grams, which is just going to work out to be 10 to the minus 6th. Okay, a part per billion, that would be 1 microgram per 1 kilogram, and that's going to be 10 to the minus 6th grams over 10 to the plus 3 grams, which is 10 to the minus 9th, and then part per trillion would be 1 nanogram per 1 kilogram, which would be 10 to the minus 9 grams over 10 to the plus 3 grams, which is going to be 10 to the minus 12. All right, and that's an N right there. Okay, so again, if you're just trying to help visualize, if you, let's say 1 kilogram of substance, that means if you have a part per million impurity in there, that means that you have 1 milligram of that particular substance in there. If you have a part per billion, that's going to be, a microgram. So a milligram, again, that's going to be a couple of grains of salt over there. A microgram, maybe that's a couple of cells, and a nanogram, that's, maybe like a cell or so. So it's just going to be very, very small amounts. And a lot of times, if you're talking about impurities and for pollution, you might be seeing these parts per million, parts per billion, parts per trillion. Now, how they set, the standards, what is acceptable, there's a lot of experimentation to see, how much can actually be detected. Okay, so this is talking with the parts per million, in terms of the mass here. If we're interested in terms of volume, for instance, we would be doing this in terms of liters. So, for instance, the part per million for volume would be 1 micro liter per liter. Also, it could be written as 1 milliliter per cubic meter. Okay, so 1 milliliter, that's going to be 10 to the minus 3 liters. And 1 cubic meter is going to be the same thing as 10 to the plus 3 liters. So that's just going to give us our 10 to the minus 6th again. The ppb, in terms of volume, that's going to be 10 to the minus, oops, I want to write this as 1 microliter per 1 cubic meter. So that's going to be, again, same thing like we have here, 10 to the minus 6th liters per 10 to the plus 3 liters. It's going to be 10 to the minus 9. And then we could do part per trillion volume, and that would be 1 nanoliter per 1 cubic meter, which is going to be 10 to the minus 9 liters per 10 to the plus 3 liters, which is 10 to the minus 12. Final little example here. Let's say we have an ore. So we're going to be some miners. And this ore has 6 part per million, and this is going to be by the weight over here of gold. So how much ore do we have to actually mine here to get 1.0 ounces of gold if we have 80% yield? So if we just look at this and just try to visualize what we have. So here's going to be our little ore sample that we're going to have. And in this ore sample down here, that's going to be my gold. So this is going to be my entire thing. So right up here, this is the ore. That's going to be my gold, okay, which is going to be 6 ppm. And when we take this gold out, so this is going to be your little block of gold right here, well, only 80% is going to be recovered. Now, I don't know if this is accurate. I'm not a miner, but it seems like a reasonable thing. So in other words, your ore gets processed and 20%, just happens to go by. So we want to figure out, we want to get 1 ounce of gold. How much of this ore do we actually have to process here? All right. So remember the 6 ppm, and since this is going to be in weight, that's just going to be 6 times 10 to the minus 6 over here. Our 80%. That's the same thing as 0.80. And 1 ounce is actually 28.35 grams. Okay, and this conversion over here, ounces to grams, I would give that conversion, so don't worry about memorizing that one. Okay, so right here, this is our subset. We want to figure out how much is this of the whole. So this is going to be 28.35 grams divided by my 6 parts per million, and this is going to work out to be 4.7 times 10 to the 6th grams of ore. And of this, remember the 80% of this is actually going to be recovered. So we're just going to go here and say that 4.7 times 10 to the 6th grams of the ore divided by my 0.80, which is going to give me 5.9 times 10 to the 6th grams. And just to figure out, this into more convenient units, we can always just convert this and say, well, 1 kilogram is 10 to the 3rd grams. And that's going to tell us how many kilograms. And we could also just go to metric tons. So 1 metric ton here is 10 to the plus 3 grams, or sorry, 10 to the 3rd kilograms. And that's 10 to the 3rd, 10 to the 3rd, that's going to be 10 to the 6th. We're dividing that by our 10 to the 6th over here. So that means we're going to have about 5.9 metric tons of ore. So that's how much ore we'd actually need to process to get that 80%. Now, again, remember here, this is going to be that subset of the subset, so these numbers should be getting bigger, which is good. The other way we could have figured this out, and really it doesn't matter because multiplication is commutative, is we could very easily just go here, our 28.35 grams, and then we divide by our 0.8, and that would tell us how much gold is actually going to be in this ore. And then we could just divide that by our 6 parts per million and figure out how much ore, and we get the exact same answer. So it doesn't matter if I divide this first one here or divide this one over here. Either way is going to give us the exact same answer in that case. Okay, so that's basically it for this one. And we'll be seeing these, we'll be going over a few examples of this stuff in class. But that's the basics behind the percents and per mils when we're dealing with all this. So again, the main thing we just want to be careful of when we're looking at this here, remember this picture we have, oops, so if it's on camera, remember this picture that we have here is that, this thing is going to be less than the whole thing when we're dealing with this. If it's not, then you've gone about it the wrong way. So you just think about this, and that will definitely help you a lot when you're calculating these things.